to get us to Mars. I don't
let's
care
move
about
on
banning
to
Twitter
the
handles.
best science corner ever. So, according to sources, scientists working for the U.S. government have achieved a net energy gain in a fusion reaction for the first time.
Not net energy gain. Get it right. We had ignition energy, which is very different from net energy gain.
Okay,
But
hold
keep
on.
going.
I know that you're in the anti-camp. Please let the science nerd have his moment.
You have to say it correctly so that people understand what you're talking about.
Let me just make it even simpler then. Explain to us what fusion is, Dr. Friedberg, and explain to us why this could potentially change everything.
We did this on a show once before, but I'll kind of do a quick kind of summary again. Basically, if you take atomic nuclei, which are made of protons and neutrons, and they repel one another, right? Because protons are positively charged, so they want to push apart from each other. So with enough energy and enough density, meaning that they're moving fast enough and they're close enough, they'll overcome their repulsion and jam into each other. And when that happens, some energy is released because the total mass of the fusion of those nuclei is actually less than those nuclei when they're on their own. And so some energy is released, and that energy drives a chain reaction. And so fusion is this concept that is fundamental to physics and fundamental to the energy driver of our universe. So the star in our sky, the sun, is driven by fusion, and only about 15% of the mass of the sun at the center is dense enough to actually drive fusion. So the big challenge with fusion is how do you get these atomic nuclei close enough together and moving fast enough that they'll actually fuse and release energy. And that's super hard. The reason it happens in the sun is because the sun has so much mass that the gravity pulls all those particles together. They get close enough, they get hot enough, they move fast enough, and fusion happens. Boom, all this energy comes out, and every day we're warm. Now, to do it on Earth is very difficult. But if we can do it, what happens when you fuse nuclei together is you don't release this isn't like a radioactive fission reaction. You release energy that can be harnessed to drive our systems, our technology.
How is it done?
Yeah. So in the 1950s, this was theorized, hey, we could do fusion on Earth. We got to get a really, really dense plasma, meaning the atomic nuclei and the electrons have kind of gone off the atoms, and it's just the nuclei spinning apart. You got to get them to move super fast, like tens of millions of degrees Celsius, and you got to get them really close together. So how the heck can you do this? So there's a couple of concepts to do this, one of which is called inertial confinement, which is where you basically create a little pellet of the material you're going to try and get to fuse, and you put a ton of energy on the outside, and you compress it really hard, really fast. And when you compress it really hard, really fast, and you can get it to be done in a perfect sphere, and you can get it to collapse on itself very quickly without, kind of shooting all over the place, enough of those particles will come close enough together, fast enough, hot enough, and they will start to fuse. Another way is through magnetic confinement, where you use magnetic fields to create a really hot plasma, get it to spin around or to move, and then the magnet brings that super hot plasma closer and closer and closer together until all those particles are moving fast and they're dense enough that they start to fuse. So, one is called magnetic confinement, the other one's inertial confinement. And so what we saw happen this week is at the National Ignition Facility, which is a facility that was built starting in 1997, and they've spent about $3.5 billion to date. They demonstrated a net energy output from the fusion reaction of an inertial confinement system. And what that means is they took a little pellet, and that pellet was made up of deuterium and tritium. The atomic nuclei that they use, the particles that they use, are deuterium, which is a proton and a neutron stuck together, and then tritium, which is a proton and two neutrons stuck together. And the reason they use those two combinations is of all the different ways you could fuse nuclei together, this has the best energy output of any kind of reaction.
Friedberg, what actually happened this time that made this work for what apparently only $3 billion? You said you didn't say 3 trillion. You said 3 billion.
About a third
of what Sam Bankman fraud stole. We have done something here, allegedly. So what actually happened that is so dramatic that we have a press conference, everybody's losing their mind?
So I just wanted to highlight one more thing about why this is so hard. You have to get such an incredible density. You have to get incredible energy. So high temperature and high density, that confining those atoms and not letting them escape and basically dissolve before they fuse is super difficult. it requires so much energy in such a controlled way, in such a perfect and precise way, that all of the digital technology, the magnets, all the measurement systems, all the software, it's taken us decades to get everything that allows us to do this today. And now we're at the point that we may be able to start to realize production scale kind of versions of this. So what they did is they had a small deuterium and tritium pellet, and they shone 192 lasers onto this container that held that little fuel. Those 192 lasers, the whole thing happened in a billionth of a second. The lasers pulsed, boom, here's an image of it. And as they did that, they, basically X-rays kind of hit the sphere, this little BB, if you will, BB kind of thing, and compressed it. And it compressed so quickly and with such heat, and it didn't dissipate because it was done so precisely. All the lasers hit at the exact right time. Boom, this thing compressed. And then energy came out, and the energy that came out that was measured was 1.5 times the energy that kind of went into that reaction. And here's a chart that I'll show you from the National Ignition Facility, which shows just how inefficient the system still is. And this isn't even speaking to Chamath's point, but basically these guys lose 90% of the energy that they put into the center of the system. Only 10% is actually used to drive the compression. The rest of it is lost, and there's a lot of ways to improve the efficiency of the system from here. But basically, they put 2 megajoules in, they got 3 megajoules out. And so it was the first proof point, production proof point, in the 70 years that we've been theorizing about nuclear fusion here on planet Earth, that this is possible and it's real. Now, this is these kind of inertial confinement systems. There are 33 private technology companies today that have raised about $3 to $4 billion so far this year to pursue several other technologies besides what the National Ignition Facility is showing to try and build production-ready versions of nuclear fusion. And so these 33 companies are using a bunch of different types of tools, one of which is the tokamak. If you show the image, I'll show you this one.
There it is.
Yeah, tokamak. This is what we talked about.
That is the magnetic spinning thing that looks like Iron Man's arc reactor, which I think they based it on. Yeah.
Yeah, you create a plasma. You basically speed up the hydrogen nuclei super fast, these deuterium and tritium nuclei super fast. And then you use magnets. And the magnetic field has to precisely squeeze the plasma, squeezing it. And if it's slightly off in even the tiniest way, think about a balloon, right? If you put a pinhole in a balloon, everything escapes from the balloon.
Yeah, you got to do it perfectly.
That's how technically hard this is. You're basically trying to create a balloon with a magnetic field, and you're trying to keep the gas, and you're trying to make it smaller and smaller and smaller. And if any tiny hole emerges, the entire plasma shoots out.
Now that they've done this,
is that what happens in Uranus?
Like when you're trying to hold in the wagyu. Anyway, let me ask this question then about the consistency of this, and then we'll go to you, Chamath. Can they do it consistently, or do you think this is like they got lucky once, or are we going to be sitting here a year from now and they're like, we put in 2 and we got out 6, and we did it 5 times?
Yeah, so now we've proven that humans can do this, okay? Which is, look, I mean, I want to give you guys some, and I know kind of some of Chamath's concerns, which is how
humans can recreate the sun, is what this comes down to?
Guys, I want to just say one, important...
Not even close.
I want to say one important thing from a historical context. All breakthrough technology starts out seeming impossibly large, impossibly expensive, and impossibly slow. The Human Genome Project 20 years ago cost $100 million to sequence the human genome. Today, we can do it in a couple of minutes for $100. Okay?
Incredible.
The first computer, the ENIAC computer, had 500 flops of compute capacity. It filled a room. It cost $8 million to build. 20 years later, we had a mainframe. 20 years later, we had a PC.
No, this is all this emotional bullshit. You're using the wrong examples.
Okay, let him finish, then you go, Chamath. Good. Finish your sentence, Friedberg, and then we go.
And today we have an iPhone that can do 2 trillion flops of compute in your pocket. I think that what we're seeing with fusion today is similar to what we saw with the ENIAC computer in the 1950s, which is the demonstration that compute is possible. And now we're seeing a demonstration that fusion is possible. Okay. And a lot of folks have anticipated this moment, and they've invested ahead of this. Now, I don't know if any of these companies that are currently kind of being built are going to be production ready anytime soon. My estimate is that we will see production demonstration of fusion in the 2030s. So call it 8 years from now plus. and then you'll see grid scale up in the 2040s. So this isn't something that's going to happen next year or 2 years from now.
It's already happening. What are you talking about?
Okay, now, Chamath, your rebuttal?
Oh my God.
Knowing you're a huge fan of solar.
This is the most navel-gazing, head-up-your-ass scientific bullshit I've ever heard.
Okay.
Couple points. Let's start with the basics. The first is that there was no previous technical analog.
Why are you angry at me?
I'm not angry. I find this so tiring hearing this. It's all syrupy nonsense.
You seem a little triggered. He's right.
Yeah, why are you so angry? Like, I don't get it.
Because I don't find this intellectually honest.
Okay.
I find it deeply intellectually dishonest.
But let's keep the emotions.
Let me finish. Let me finish. Okay. When you talk about sequencing the genome, there was no alternative. So you're right. It was an enormous technical leap forward. When we built a computer, there was no analog. It was an enormous technical leap. And so you're right. We have a cost curve we don't understand. And then we iterate as rapidly as possible in all these innovations where we built an entire infrastructure to ride down the cost curve. The thing is, fusion energy exists today. It's called the sun. We actually know how to capture it at virtually no cost right now. So according to the IAEA, today you can capture grid-level solar energy for about 3 cents a kilowatt hour. That's as close to zero as we've ever been. And over the next 10 years, their forecast is it's going to get to 1.5 cents. If you then want to store it and you layer in storage costs, we'll be at a whopping 3 cents a kilowatt hour. That's where we are today. And so I think that fusion does exist. I do think that this is an incredible technical leap to replicate something that exists. And I think that's where the intellectual dishonesty is. It does exist. It has been captured. It can be harnessed. And there is a positive energy equation, just in a different modality that doesn't speak to these technically minded individuals. A couple of other points about what I saw. I think it's incredible what happened, okay? But just to make sure we're clear, this is 192 lasers, the size of 3 football fields, that consumed 322 megajoules of energy, which then ultimately delivered 2 megajoules to a target, which then released 3. So this is why I'm saying we had positive, what's called ignition energy. We did not have positive electrical energy captured. So yeah, could we figure this out? Absolutely. Can we then shrink the 3 football fields down to something that looks the size of a laptop? We possibly could. Will it take 20 or 30 years? Possibly. But in the meanwhile, if the goal is unlimited costless energy, you're on that cost curve already.
Yeah, but why can't it be both? So you said I was being intellectually dishonest. What was I intellectually dishonest about?
What's dishonest?
Yeah.
You're comparing
I'm saying what you're saying is right. Yes, you can get.
You seem to be in agreement.
Industrial scale,
I just think that you're trying to say that this is an entirely new thing. No, it's a different approach to a thing we've already beaten and basically captured.
What I would argue, Chamath, and I think this is important, the net energy you can capture on, say, a football field sized facility from solar is, a tiny fraction of the energy you could generate from a football field sized fusion reactor. And that's why the argument would be like, hey, when we were developing computers, hey, we have abacuses, we shouldn't be developing computers. And I think that's the analogy I would use here.
This is why the cost per kilowatt hour is what the levelized cost of energy tries to do. It tries to normalize that argument away, because everybody would say that, hey, hold on a second, you're going to need planefuls of this or boatloads of that. And people said, no, what's the levelized cost of energy? What is the cost per kilowatt hour to generate energy? And what I'm saying is that is an absolute scale, and free is 0, and we're at 1.5 cents already.
Here's what I would say. JCal, one sec. Chamath, the opportunity here is not necessarily about cost reduction. It is about scalability. And if hydrogen is abundant, which it is on this planet, it is nearly infinitely abundant. We can take that hydrogen and we can scale up energy and electricity production in a way that is unimaginable compared to solar. And I don't think that solar should be excluded. Solar is key today and should be scaled up. And I'm 100% in agreement with you. But the scalability to go 100x, if we want to make 100 times more electricity, I think we need fusion. And I think that it's feasible.
So I think we have reached a good settlement here. Chamath, you're saying, hey, listen, we're getting solar down so cheap, we can solve
Not
this
solar,
problem.
all forms of energy.
Okay, great. We are solving that. So for our needs today, and then what Friedberg is saying, but what if you had unlimited, a thing that we can't even imagine? Beautiful. Now, watch